In this video, I will go over all the predicted topics and questions for Paper 2, AQA A Level Chemistry Exam 2025. Paper 2 is about the physical chemistry and organic chemistry, with the majority of questions are about organic chemistry. So I'm going to start off with the most common physical chemistry topics that come in the exam. The first topic here is the Arrhenius equation. Arrhenius equation is very common in Paper 2. Over the last 4 years, it has been in the exam, although last year it was in Paper 3, not in Paper 2. So in Arrhenius equation, they're going to give you the equation. Just remember, in this equation, Arrhenius equation, link between the rate constant for the reaction, the activation energy, and the temperature. The activation energy here is in joules and the temperature is in Kelvin. And then they will provide you with one of the three equations, either the first one here, or they could give you this equation, the second one, or the third equation. If they give you this equation, the third equation, which links between the natural logarithm of the rate constant and the temperature, they will give you this curve, which is the between the natural logarithm of the k and 1 over t. Here, they can ask you to calculate or find the activation energy, and then you can find that from the slope or the gradient of the curve, because the slope equals minus EA over R. And R here is a constant, is the gas constant, which they're gonna provide you with. EA will be in joules. They could give you also this equation, the second one or the first one, and ask you to either calculate the activation energy or the temperature. So these are the type of questions that have always been in the exam. Either calculate the temperature using the equation, remember, please make note whether they ask you to find the temperature or calculate the temperature in Kelvin or in degrees Celsius. Calculate the value of the natural logarithm of k using the equation provided, or calculate the activation energy from the graph. The second topic is irreversible reactions, a position of equilibrium and equilibrium constant. So as I heard that there was nothing about the gas equilibrium in paper 1, so it's very possible that, or very likely that in paper 2 they will ask about the equilibrium constant Kc, because they use the exact same principle here and for the Kp. The only difference is in Kc we use the concentrations, in Kp we use the partial pressure. So this is the equation we're gonna use for the calculation of the Kc. In the exam, they will either provide you with the concentrations or initial moles and the for one of the reactants or all of the reactants, and the moles of one of the chemicals, whether it's one of the reactants or one of the products at equilibrium. And then you would need to calculate the number of moles of all of the reactants and products at equilibrium using the balanced equation. Then calculate the Kc and its units as well. Remember that the unit for Kc will always differ depending on the number of moles of products and reactants. And then the factors affecting the position of equilibrium. The most common one is the temperature. So they like to ask about the effect of temperature on the yield. So that will, of course, depend on which direction of the reaction is exothermic. So if we have the forward reaction is exothermic and you increase the pressure, you increase the temperature, then the reaction will favor the reverse reaction or the endothermic side of the reaction, and vice versa. The concentration, but they don't tend to ask about the concentration in your exam. Also, the use of catalyst, it's not very common to ask you, but just in case, the use of catalyst will increase the rate of both the forward and reverse reaction, so it doesn't affect the position of equilibrium. Please remember that temperature will affect the Kc, but the concentration will not affect the Kc. The most common type of question that you will encounter in this topic will be calculating the moles at equilibrium, and this is a representative example here for a reversible reaction, hydrogen iodide to give you hydrogen and iodine. So if they give you the initial moles for the hydrogen iodide, let's say it's Z, and then they give you the mole number of moles of one of the products, which is the hydrogen at the end, which is Y, then because hydrogen and iodine, both of them 1 mole, or it's 1 to 1, then that means the number of moles of iodine as one of the products at equilibrium will be exactly the same like hydrogen, and the number of moles of the hydrogen iodide at the end will be Z minus 2Y, because 2 of the hydrogen iodide will give you 1 mole of the hydrogen. So they can ask you to calculate the moles at equilibrium. Well, they will ask to give the expression of Kc to calculate the Kc and its units. So remember, when you calculate the Kc, we are dealing with concentrations, not number of moles. We only use number of moles if the Kc doesn't have any units, or basically if the volume for the equation is exactly the same at the top and the bottom of the equation, like this one. So there are 1 mole of the hydrogen and so it's going to be hydrogen times the iodine over the hydrogen iodide squared. So that means that here we can use the moles instead of the concentration. Remember, when you calculate the concentration, when you use the volume, you use the total volume. So if they told you that there are 2 different reactants and they added the X volume from the first one with Y volume of the second one, then you will have to, when you calculate you calculate the concentration in the total volume. And then they tend to ask as well on the about the effect of temperature on the yield and on Kc. Rate of reaction and calculation of order, one of the most common topics in paper 1. However, the Maxwell-Boltzmann distribution curve is not very common in your exam. It only featured one over the past 5 years. However, the question when it comes in the exam is quite typical. So they tend to ask you to sketch a graph for the Boltzmann distribution curve for 2 different temperatures or 2 different concentrations. So remember, when you draw the curve or when you sketch this curve, first of all, the label of the X and Y axes. So the X axis will be the activation, will be the energy or kinetic energy, and the Y axis will be the number of molecules or number of particles. And then if we have 2 temperatures, then the curve will be more skewed to the right by the increased temperature, like the green one here. So because there are more particles that have higher, more particles will have higher energy, more than the activation energy. This is why the temperature, increase in temperature will increase the rate of the reaction. Remember that when you sketch this curve, make sure that the area under the curve stays almost the same for both curves. In case of the use of the catalyst, it just postures the activation energy to the left, because it lowers the activation energy. And then for the concentration, for higher concentration, the curve will be higher than the curve which is of the lower concentration. So this green one is for the increased concentration. And then the calculation of the order of the reaction. This question is a typical question in paper 2. It will always be in paper 2, but it can come in different format. Over the past 2 years, the question has been came as providing you with a table, incomplete table with the concentration of the different reactants and the initial rate, and ask you to complete the table, calculate the K, and so on. So first of all, let's go over the basics for this topic. So the rate, constant, and order. So zero order means that the rate doesn't change if the concentration of the reactant it changes. So it's going to be a straight line, and because the straight line for the change in the concentration of the reactant with time is a straight line, meaning that the gradient doesn't change, the rate doesn't change with changing concentration. First order is when the rate is directly proportional to the concentration, and second order means that the rate is directly proportional to the squared of the concentration. To calculate the order, all the concentrations are kept the same except one reactant only that will change. And then you notice after you change that reactant, if the initial rate doesn't change, that means that it's zero order. If the change is the same, meaning if when the reactant is doubled, the rate was doubled, then it's going to be first order. And if the concentration changes by a factor of X and then the rate changes by a factor of X squared, then it's going to be second order. This factor of change can be calculated as the new concentration divided by the original concentration. Remember the rate determining step, because it's very common to ask you about evidence for the rate determining step. It's the step that has all the reactants that affect the rate. So this is a practical example for the table that provide you in the exam. So if we have rate equals K, which is the rate constant, times the A squared and B, which means it's a second order for A and it's first order for B. Then for reactant A, the initial concentration 0.1 and the B is 0.1, and that was the rate. If the concentration of the first reactant changed into 0.15, meaning it's changed by by a factor of 1.5, kept be the same, then the rate will change by a factor of 1.5 squared. So you multiply the initial rate by 1.5 squared. And then if the change the reactant A from zero point 0.1 into 0.03, so it changed by a factor of 0.3, and the reactant B changed from zero point 0.1 into 0.2, so changed by a factor of 2 because it's first order for B. Now we have to multiply this by 2, and then it's second order for A, so multiply this by 0.3 squared. The type of questions that you may encounter in this topic, which have been a collection of all the questions over the past 5 years. So they can ask you to complete a table for the concentrations of the different reactants with the initial rate. They can ask you to calculate the K and give the units. And they ask you to provide evidence for the rate determining step. They don't usually ask you to propose a mechanism for the reaction. They just ask you, they will give you the mechanism, and they ask you to propose which step is the rate determining step and provide evidence for that. So the evidence is always that the reactants, which are mentioned in the rate equation, they have been involved in the rate determining step. Calculate the rate when the reactants are halved or doubled or whatever. We can ask you to calculate the rate if one of or another of the reactant changes. Plot a graph of a volume versus time, so they can give you the values for a specific experiment and ask you to plot the graph, or explain how the graph show that reaction is zero order, like this one. So if you plot for example, the volume or the concentration versus time, it's going to be a straight line, which means that the reaction is zero order because the gradient doesn't change, which means the rate doesn't change with the concentration. Use a graph to determine the initial rate. The enthalpy change, calorimetry, and Hess's law, these are all the thermodynamics topics that can feature in paper 2. The most common one of these is the calorimetry, or the calculation of the enthalpy of combustion using calorimetry. Remember the equation that you're going to use in this equation, in this question, which is Q, which is the energy transferred here, equals mc delta T. Delta T is the change in temperature. It can be in degrees or in Kelvin because the change is the same. It doesn't really matter. And then M is the mass of the water in a gram, and C the specific heat capacity of water, which is going to be provided to you. Remember that the Q here that you calculate is going to be in joules. And then when you calculate the delta H, it's going to be equal Q over the number of moles that caused the temperature change. So the Q here in this equation has to be changed from the joules into kilojoules because delta H is in kilojoule per mole. So you have to change it from a joule into a kilojoule. And remember as well that the delta H for combustion has to be with a negative sign. So you have, when you do this equation and calculate the delta H, you have to add the negative sign to the Q as well. Enthalpy change using bond energies, one of the topics that only featured one in paper 2 over the last 5 years. However, this is should be an easy question because we calculate the enthalpy change by calculating the total energy gained to break all the reactant bonds minus the total energy lost to form all the products bond. So it's not very common, but please, when you answer, if this question features or comes and you answer this question, try to answer it stepwise. So if you make any mistakes, it's not carried forward. So try to make a calculation for the total energy gained to break all the bonds of the reactants as one thing, and then the total energy to lost to form the products as a second line, and then the delta H at the end. Hess's law. So Hess's law is not also very common. I think it came only once over the last 5 years. But just in case they decide to bring it this year, remember we already covered the Born-Haber cycle in paper 1, and as I heard, it wasn't actually in paper 1 this year. So they may decide that we're gonna bring Hess's cycle in paper 2. So Hess's cycle uses the same principle. So the total enthalpy change is independent of the pathway. So you have to find either they use the enthalpy of formation, standard enthalpy of formation, or the standard enthalpy of combustion. You just need to construct the cycle, find with the direction of the arrow which one is root 1, which one is root 2, and find the missing enthalpy change. One of the common questions about calorimetry as well, by the way, is the reasons why the enthalpy change from the of combustion using the calorimetry is less exothermic. And this is because of the loss of heat during the experiment due to the evaporation of the fuel that is combusted, and then due to the incomplete combustion, because some of the fuel can undergo incomplete combustion in addition to the complete combustion, and incomplete combustion is less exothermic. And this is the Hess's cycle law. Shape of a molecule. So there are only two possible shapes that can appear in paper two. The first one is a comparison between amines and ammonium. All right, so amines will have three bonding pairs and one lone pair. So the shape is going to be pyramidal and the bond angle is 107. For the ammonium ion, it's going to be tetrahedral because we have four bonding pairs with no lone pairs, and the bond angle is 109.5. The other shapes that you may see in the exam is a comparison between the shape of an organic molecule that has a carbon with a double bond, either something like the carbonyl compounds or like alkenes. In this case, the shape is going to be trigonal planar, and the bond angle will be 120. This is compared to the normal carbon that has four different bonds, where the shape is going to be tetrahedral with bond angle 109.5. So why this shape has this bond angle and why is it planar, even though there are four bonding pairs, but there are only three areas of bonding because the double bond is here one area for the bonds. So the shape is going to be as if we have only three bonding pairs, even though we have four, and the bond angle will be 120. And this is the reason why when you react or you do the nucleophilic addition to the carbonyl group for the aldehydes and ketones, you could end up with a racemic mixture of two of the isomers, which are the optical isomers, because the nucleophile can attack from any side because this is planar. So they can attack from here, from there, or from that side. So this is one of the questions that came before in the exam, and you should know that this is because this is planar. Forces of attraction. So the forces of attraction is quite common in paper two because it has a lot of application when it comes to the organic molecule. So the first thing that you need to know about this is related to the electronegativity, the inductive effect. So electronegative atoms like fluorine, chlorine, and bromine will increase the reactivity or increase the acidity of organic acids or weak acids or organic acids. This is because they are electron withdrawing groups. They have negative inductive effect, so they will withdraw the electrons or pull the electrons toward them, and they will weaken the OH bond, making it easier for the acid to lose the hydrogen and will increase the acidity of the acid. And then the alkyl groups, on the other hand, or the carbon, they have the opposite effect. So alkyl group, they have an electron donating effect or they have positive inductive effect. So they tend to push the electrons towards the adjacent atoms. So if you have more of these carbons or alkyl groups next to a nitrogen, the nitrogen will have a lone pair of electrons, then that will increase the basicity of the amine. Increasing the basicity here is due to the increase of the availability of the lone pair of electrons on the nitrogen. So the nitrogen or the amine will be more basic. This is the answer if they ask you to compare between primary and secondary amines, for example, in terms of basicity, or to compare between aliphatic and aromatic amines, which one is more basic. These type of questions are very common in paper two. Remember that also because alkyl group will push the electrons away from them, or they have positive inductive effect. They will reduce the electron deficiency of adjacent carbon. So if you have a carbonyl group, and then for aldehydes and ketones, the aldehydes will only have one adjacent carbon. The ketone will have two adjacent carbons on both sides of the carbonyl group. So they will tend to reduce the reactivity of the carbonyl group towards the nucleophilic addition reaction because they decrease or reduce the electron deficiency of the carbon. So that was a question a couple of years ago when they asked what do you expect to happen when they used a ketone instead of an aldehyde for a certain reaction, and they asked you what do you expect for the rate of the reaction. Do you expect it to be faster or slower? So it's going to be slower for a ketone. Remember the strengths of the bonds. They come in order, of course. Covalent bonds, ionic bonds are are the highest, and then we have hydrogen bonding, which is a stronger type of bond than the permanent dipole forces of attraction for polar molecules, and which are more than the van der Waals. The hydrogen bonding, any molecule that has hydrogen bonding, like alcohols or carboxylic acid, will have higher melting points and boiling points than the ones that do not have these type of bonds. So organic molecules, usually we see the hydrogen bonding and we see the van der Waals and the dipole-dipole interaction. Of course, the hydrogen bonding will be between the hydrogen on the nitrogen or oxygen only, and a nitrogen or an oxygen. And for the last 5 years, they maybe asked once to draw the hydrogen bond, so they might ask you this year to draw the hydrogen bond. Please remember how to draw it, how to show the hydrogen bond between the lone pair of electrons of the partially negative oxygen or nitrogen and the partially positive hydrogen, which is linked to another oxygen or hydrogen for another molecule. The mass skills, so there will be some questions with mass skills in paper 2, not as extensive as paper 1, but there will definitely be some questions. So this is the ideal gas law. Sometimes they get you questions where you need to calculate the number of moles of gases using the ideal gas law, even though it came this year in paper 1, but it's still possible to come in paper 2. Remember, for the ideal gas law, the pressure here is in Pascal, not kilopascal. The volume is in a meter cubed, so they usually will give you the volume in centimeter cubed. So you have to multiply this by 10 to the power minus 6. And then N is the number of moles, and T is the temperature in Kelvin, not in temperature, not in degrees Celsius. And then calculating the number of moles using either the mass and the MR, or by the use of the concentration and volume, because you're going to use these equations in your exam. Sometimes they ask you to calculate or to find the mass that was produced from a certain reaction if the percentage yield was like 85%, for example. So remember that the percentage yield and the mass of the product actually made over the maximum theoretical mass of the product. Moving on to talk about organic chemistry topics and predicted topics and questions. The first thing is the analytical techniques, because this is a guaranteed question in your exam. You will have to use data from the IR and carbon-13 and proton NMR to find a particular structure. For the IR, the most important peaks in the IR that usually come in the exam are the carbonyl group here, which is a strong and sharp peak at 1720 centimeter minus 1. And then we have the OH peak, which is going to be broad. You need to be able to differentiate between the OH that comes from an alcohol and an OH that comes from a carboxylic acid. It's going to be an OH anyway, and it's going to be broad. So the OH of the alcohol will tend to be at more than 3000, so around 3300, like this one. So this is an OH of an alcohol. If it's an OH of an acid, then you will see it a bit to the right. So it's going to be below 3000 or around 3000. That's for the carboxylic acid. They tend to ask you about the how to differentiate in the IR. What is the difference you're going to see in the IR for a certain reactant and a product? So you need to look at the functional group, and you need to look for the peaks that are changing. For example, the cyanide group, and if it changes it into an amino group, for example. So you're going to use the data book to identify what peak would you see for the cyano group, what peak would you see for the NH2 groups, for example. And always refer to the fingerprint region, because the fingerprint region will change, which is the part at the right-hand side of the spectrum, IR spectrum. So the fingerprint region will always be different if you do any small change in the structure. So always refer to the fingerprint region, and you compare it with a data book. And then moving on to the carbon-13 NMR. So carbon-13 NMR, we usually use it to find the number of non-chemically equivalent carbons. The number of non-chemically equivalent carbons will equal the number of the signals that we see in the carbon-13 NMR. For this one, there are 4. So simply count the number of the signals. And then we can use the carbon-13 to differentiate between aldehydes, ketones, carbonyl group, and the carbonyl group that comes from acids and esters, because is the aldehydes and ketones, will be over or more than 200 part per million, and the ones from acid and ester will be below the 200. Also, we can use it to, or we can easily identify the carbon which is adjacent to an oxygen or adjacent to chlorine. The carbon adjacent to the carbonyl group as well, usually around slightly above the 20, and the one which are carbon adjacent to carbon will be at the far right, which is normally less than 20 part per million. And then moving on to the most important one, which is the proton NMR, because there's usually a very big question with the proton NMR where they ask you to explain and interpret the data and give explanation for all of the peaks. So what do we normally look at for the proton NMR? So first of all, using proton NMR, we can determine the number of chemically non-equivalent protons. So this is the number of the signals. For the table that you can see here, there are 4 different signals, which mean there are 4 chemically non-equivalent protons or 4 chemically non-equivalent hydrogens. And then the integration value here will give you the number of protons which are responsible for that particular signal. So if the integration value can either give you the actual number of the proton, or it could be just a ratio between the protons. That will depend on when they provide you with the molecular formula, you count the number of hydrogen. If the total number of hydrogen from the molecular formula equal the total of the integration value, then the integration value is exactly the number of protons. So here, as we can see, so we have 3 protons that give you the signal at 1.2 part per million, 3 protons at 2.1, 1 proton 3.7, and 1 proton for 3.9. And then the chemical shift, so the chemical shift in part per million, that we use this the data from the datasheet they provide you with to identify the most probable chemical environment. So you're going to identify whether your carbon, the protons is on a carbon and adjacent to it is another carbon or a carbonyl group or an oxygen or like an electronegative group like chlorine or bromine. So this is how we identify the chemical shift. So the chemical shift gives us information about the adjacent atom itself. And then the splitting. So the splitting here, as you can see, which could be quartet, singlet, or doublet or triplet, will give us information about the number of the protons on the adjacent carbons. So the if we don't have any protons on the adjacent carbon, it's going to be a singlet. If we have 1 proton on the adjacent carbon, then it's going to be doublet. If we have 2, it's going to be triplets, and so on. So even if you don't figure out the correct final structure of your compound, that's all right. As long as your interpretation is correct, you're gonna get most of the marks. So don't worry if you don't get to the final structure, but you did the interpretation well, then you're gonna get most of the mark. So if we look at this example here, the chemical shift here for the first one is 1.2, and it's a doublet, and it's 3 proton, which means it's a CH3, or it's a CH3 because there are 3 protons. And adjacent to it, there is a carbon which has 1 hydrogen. And also this is from the chemical shift, it's just a carbon adjacent to it. So you have to analyze it step by step. So you have to analyze the chemical shift, the splitting pattern, and the integration value. And then we have the 2.1 here. This is most probably is a carbon adjacent to a carbonyl group. So a carbon hydrogen adjacent to a carbonyl group. And it's a singlet, which means it doesn't have any adjacent hydrogen on any other carbon. So there is no hydrogen, and there are 3, so there are 3 hydrogens next to a carbonyl group. And then the carbon, which is the carbon hydrogen, which is adjacent to an oxygen, the chemical shift is between 3.5 and 4.5, and so on. So you don't need to memorize these. You just need to use your data sheet to identify the different one. And as we said for the splitting, this is, for example, quartet, which means there are 3 adjacent hydrogens. This is singlet, no adjacent hydrogen. This is singlet, no adjacent, and this is doublet. So there are 3. There is 1 adjacent proton. Organic chemistry reaction mechanism, a lot of mechanisms in your exam. The rule of thumb when you draw the mechanism, remember that the curly arrows will always go from the electrons to an electron deficient atom or towards a single bond to make a double bond. So it shows the movement of electrons. You have to draw the electrons except for the double bond. So when you have a double bond, you don't draw a lone pair of electrons. But if you have an atom, even if it has a negative charge, you still need to put the lone pair of electrons and move the lone pair of electron, like oxygen, for example. So if you have an OH with a negative charge like this, so you have to put the lone pair of electrons and show the movement will be from the OH, let's see, for example, towards carbon like this one, and then we're going to break this bond between the carbon and the bromide. There will be several reaction mechanisms in your exam. There will be questions with missing arrows, and there will be an organic tenses reaction where there are multi-step ones, sometimes with a missing intermediate or a missing product in the multi-step reaction. And there will be a whole mechanism question when they ask you to draw the whole mechanism. Remember that when you draw the mechanism, when a bond is added, another has to be broken at the same time. And there's only one exception here, which is for oxygen and nitrogen, which can have a positively charged oxygen or nitrogen with a dative covalent bond. Like when you have ammonia or water, you can make the bond first, and then you can break the bond between the oxygen and the hydrogen, or the oxygen and the nitrogen and hydrogen at a later stage by the use of a base. But remember, if you have something like that, if you have oxygen, water, if you use the water as a nucleophile and you add it to something, then the oxygen has to have a positive charge. The next step will be the use of a base. So any base that you're going to use, that's going to take this hydrogen, this proton, and then we're going to break this bond here. Eventually, all your compound should be not charged. So I'm going to go very quickly over the different reaction mechanisms and the named reaction that you need with the conditions for each, because you're going to be asked about several of these reactions in your exam. The first one is the radical chain reaction, where alkanes are fairly inert. So we can do the substitution for alkanes using the UV light or radical chain reaction. This reaction have the initiation, propagation, and termination step. Initiation is the formation of the free radical. Propagation, where more free radicals are formed by a reaction between a free radical and a neutral molecule. And finally, termination, where the free radical formed in the reaction react together to give you the different products. Usually, these type of reactions are not clean. They tend to give you so many different products. CFC and the ozone layer. This wasn't in the exam lately, so I expect it to be in the exam this year. Of course, I haven't seen the exam, but this is my expectation. So remember that the ozone layer is important because it absorbs the UV light, which is the harmful type of light that can cause cancer. And the CFC, or chlorofluorocarbon, will destroy the ozone layer by formation of the chlorine-free radical. The chlorine-free radical under the UV light will react with the ozone to give you oxygen and another free radical, which is going to react with another molecule of ozone to give you oxygen again and another chlorine-free radical. The chlorine-free radical here acts as a catalyst because it's regenerated in the reaction. Nucleophilic substitution reaction, we have three different nucleophilic substitution reactions we need to know about. These reaction, we find them for the alkyl halides or halogen alkanes with nucleophiles. The nucleophile can either be a hydroxide, can be a cyanide group, or can be an ammonia or an amine. So with the hydroxide, remember the conditions for this one is going to be aqueous sodium hydroxide or potassium hydroxide, not the ethanolic. The ethanolic will lead to elimination, and the reaction mechanism is typical regardless what type of nucleophile you use. So usually the nucleophile will attack the carbon, which is the electron deficient one, and then the bond will break between the halogen and or between the halide and the carbon. So that's the typical mechanism. For the ammonia, the only change here, or there is an extra step for ammonia or for amines, because for ammonia or amine, what you do is that you add a neutral molecule. So you end up with a nitrogen with 4 bonds and a positive charge. So another molecule of the ammonia or amine, if you use an amine, will come and act as a base to take this extra hydrogen to give you the amine that you get. Remember that for this reaction, you can get several products because the amine formed can reattack more of the hydrogen, the halogen or the alkyl halides or halogen alkane, the haloalkanes, and then it can give you secondary amine, tertiary amines, and quaternary ammonium chloride. So it's quite common in the exam to ask you what will happen if you use excess of the alkyl halide or excess of the amine. So if you use excess of the alkyl halide, you're going to end up with mixture of primary, secondary, and tertiary. If you use only one excess of the amine, so you probably will end up with the primary amine only. Elimination reaction. So the first one for the elimination is, so elimination will give you alkenes. And there are two elimination here. The first one is the elimination of hydrogen bromide or hydrogen halides from haloalkane using the ethanolic OH to form an alkene. Here the OH will act as a base, not as a nucleophile, and it will come to take the hydrogen from the adjacent carbon, and then a double bond is formed between the two carbons, while the bromide or the halide will leave. So this is the mechanism for this reaction. Remember, for this one, the conditions will be using ethanolic potassium hydroxide or sodium hydroxide. Synthesis of the alkenes from alcohols, it's a different mechanism here because it's going to be acid catalyzed. So we are going to use an acid. The acid is going to first add to the OH, so movement of electrons from the lone pair of electrons on the oxygen toward the proton from the acid to give you this intermediate where the oxygen has two hydrogens and a positive charge, and then the water molecules will leave to give you this carbocation, and then the hydrogen on the adjacent carbon will leave to give you the alkene. Electrophilic addition reaction, these are the reactions for the alkenes with the different adducts. So what do we add in these? So we can see this with halogen alkanes, or we can add water molecules using an acid, or we can add the halogens like bromine or chlorine. So the mechanism again is a typical mechanism. So first of all, the attack starts with the double bond from the alkene towards the hydrogen, and the bond between the hydrogen and chlorine or hydrogen and bromine will break, and then the hydrogen can be added to any of these two carbons. However, if you have unsymmetrical alkene, then there will be a major product and a minor product because there is a carbocation formed here. And we can have two possible carbocations if we have unsymmetric alkene. So we can have something like this one, which is primary carbocation, where the hydrogen, the carbon here is attached to only one carbon and two hydrogen, or we can have a secondary carbocation where the carbon is attached to two carbons here. So the secondary carbocation is more stable than the primary carbocation. So more will be formed of this one than the first one because it's more stable, which leads to the bromide attacking the carbocation, this one in this case, and this carbocation in that case. So the two products can be formed. However, this is going to be the major product because it comes from the more stable carbocation. I always tell my students to remember that when you add the hydrogen, add it to the carbon that has higher number of hydrogens. So I always tell them make the rich richer. So the carbon atom which is richer or is rich in hydrogen atoms, make it richer by giving it an extra hydrogen to end up with the major product. Another electrophilic addition is the addition of the halogen, the exact same mechanism, but instead of adding hydrogen bromide, we add two bromines here. And then addition of water or hydration, this is a bit different mechanism because we are going to use the sulfuric acid or the acid. So the first step is the double bond going to take the proton from the acid, and then the bond will break between the hydrogen and oxygen to give you the carbocation. Again, if you have as unsymmetrical alkene, you're going to end up with two products, carbocation generated, then the sulfate, hydrogen sulfate ion will be added to this carbocation or will attack this carbocation. Don't forget the lone pair of electron. The arrow will always go from the lone pair of electron on the oxygen. And then finally, when you warm with water, you're going to end up with the alcohol and the acid will be regenerated. Nucleophilic addition reactions to carbonyl group. This is one of the most common mechanisms in your exam. There are two major ones. The first one is the cyanide, where the cyanide is added. They usually tend to ask you about the conditions. So when you use sodium cyanide or potassium cyanide, don't forget to say that you also use an acid. So you could use something, any acid like hydrogen chloride. So don't forget the acid in your conditions for the reaction, or you can simply say we use hydrogen cyanide, so they can accept it. The mechanism is typical where it's nucleophilic addition. So first of all, we're going to add the cyanide When you add the cyanide, remember that the lone pair of electrons will be on the carbon, not on the nitrogen. And again, the arrow will go from the lone pair of electrons on the carbon. Don't forget the negative charge on the carbon as well. Will attack the carbonyl carbon, and the double bond between the carbon and oxygen will break. We have a negative charge now on the oxygen after the addition of the cyanide. Then this electron will move. This will take the hydrogen, which is come from the acid. So the next step is the addition of the hydrogen from the acid, from the lone pair of electrons on the oxygen, to give you the cyanohydrine product at the end. Sometimes they ask you the same question, but using the hydride, which is the hydrogen with a negative charge. So you need to apply the exact same principle here, and then don't forget the lone pair of electrons. So the hydride is the one that is going to attack the carbonyl carbon. So exactly the same mechanism, it's just a different nucleophile. Addition elimination reaction, these are the reaction of acid chloride, acid anhydrides, and the esters. And with nucleophiles, they can form alcohol. The nucleophiles can be either alcohols, amines, or water. So the reaction mechanism is typical. It's as it states, it's an addition followed by elimination. So first of all, you're going to add the nucleophile to the carbonyl carbon, and don't forget to break the bond. Don't forget the number of electrons on the oxygen when we move the electrons. And then this is the addition one. So this is the first intermediate, and then this is going to be followed by elimination, where the chloride is going to leave. If you have an ester, it's going to be an R group, or OCH3 if it's like methyl ester. And then the double bond is regenerated here. So the lone pair of electron on the oxygen will regenerate the double bond. Don't forget, when you added this ester in this step here, there was the oxygen had three bonds, three groups attached to it. So it had a positive charge, and your molecule has to be neutral at the end. So you have to remove this hydrogen from the oxygen to regenerate the neutral molecule. So if you have chloride that left, the chloride can act as a base to take this hydrogen, and then we will get the ester at the end. The nucleophile can be anything, can be an amine, or could be a water molecule as well. So it depends on which one is there. Esterification is the formation of an ester from an acid and alcohol. It's usually acid catalyzed reaction. You don't need to know the mechanism, the detailed mechanism of this reaction. However, if they get you one of these mechanisms, usually they're going to get you the mechanism themselves, but they're going to be some missing arrows, and they're going to ask you to draw the missing arrows in the reaction mechanism. So it's just an acid and alcohol to give you an ester. Hydrolysis is the formation of alcohols from ester, and there are two types of hydrolysis. There is the acid catalyzed hydrolysis, where you use an acid with water to break the acid into the ester into an acid and alcohol. And there is the base catalyzed hydrolysis, when you use a base to get you the salt of the acid plus the alcohol. And that will tell us about the saponification. Saponification is basically the same reaction, but when we use the fatty acid esters with glycerol. So when you use the base, you're going to end up with the sodium salts of the fatty acids, which can be used as soap and glycerol. So this is called saponification, and it gives you the soap. Craft acylation or electrophilic substitution using the acid chloride and addition of this acylation or acyl group to benzene ring. This question has been in the exam lately, so I would expect this mechanism to be in your exam this year. So normally they tend to ask you about the catalyst that is used in this reaction, which is the aluminum chloride. So the aluminum chloride will take the chlorine to generate the electrophile that's going to be added or make the attack in the next step. So when you have the benzene ring, usually the electrons move from the inside the ring towards the carbon with the positive charge here, this electrophile. And then the second step is we're going to draw the ring, but it's going to be an open ring around this carbon atom, which has the four bonds with a positive charge inside the ring. And then the second step is the removal of the hydrogen as a proton, where the electrons go back into the ring to regenerate the ring of the electrons inside the benzene. So this is your final product, and this is this reaction. I would expect it to be in your exam this year. Also, another electrophilic substitution reaction, which is the most common electrophilic substitution in the exam, is basically the nitration. They tend to ask you about the generation of the electrophile. How is it generated? So you need to know these two equations here, how the NO2 plus the electrophile is generated. and also the mechanism of the reaction. The mechanism is going to be exactly the same like Friedel-Crafts acylation. Both of them are electrophilic substitution, the same mechanism. So as you see, the electrons move from inside. You write the ring open, the electron ring open with a positive charge inside. Then the hydrogen leaves as a proton, regenerating the full ring of the electron inside the benzene ring to give you the nitro compound. And finally, the reduction. So reduction, there are two types of reductions. The reduction of cyanide to make amines, aliphatic amines. So you can either use lithium aluminum hydride and dilute acid to give you primary amines, aliphatic ones, or you could use the hydrogen itself with a nickel catalyst at high temperature and pressure. Again, will give you primary amine. And then the other one is the reduction of the aromatic nitro group into aromatic amines. And in this case, we use 10 with concentrated hydrochloric acid. And then the second step is the use of the sodium hydroxide. In your exam, usually they want you to write about the 10 and the concentrated acid. They don't care much about the sodium hydroxide. Now, how to work through these organic chemistry synthetic schemes and how to answer these type of questions. So this is one of the past paper questions here, and it's an scheme for the multi-sensors or multi-step tensors. So first of all, you need to think of the role of each compound. You need to look at where the change has happened in the project. So if we start, this is the starting point here, and we look at the first product. What has changed? The only change here was the introduction of this nitro group. So it must be the electrophilic substitution or the nitration, which is the use of conc nitric with conc sulfuric acid to form the nitration. Step two, as you can see, the only change is the change of this nitro into an amino group, which means that we used the 10 with the hydrochloric acid. So it's reduction. And the third step was the addition of this acyl group or the COCH3. So how can we add this to the nitrogen? We can use the acid chloride through the addition elimination reaction to the nitro, because the amine will either act as a nucleophile or it will act as a base. So here it's going to act as a nucleophile because the aromatic amines are not very basic. So they will act mainly as nucleophile. To undergo the formation of the amide comes from the addition elimination of with the acid chloride. And then here, moving to step 4, as you can see, the only change is the addition of this or substitution of one hydrogen with chlorine. And the only type of reaction we can do this is the free radical reaction with chlorine. And then what happened in the next step is that we changed this chlorine into an NH2. So the chlorine, this is an aliphatic alkyl halide, and we can change it into an amine by the nucleophilic substitution reaction, but here with using the use of the ammonia. Remember that your reactions can either be substitution, addition, or elimination. There is no other type of reactions other than these three types. Remember that you look at your compound, whether it's aliphatic or aromatic. Remember to look at whether it's polar or non-polar to guide you at how to make this change. What is the functional group, how it changed. Polymers, one of the topics which are not very common, but usually for the addition polymers, when they come in paper 2, they tend to ask you to write or draw the repeat unit for an addition polymer. Remember that for addition polymers, because this hasn't been in the exam at all over the past 5 years, the addition of plasticizers for addition polymers will make the addition polymer more flexible, because plasticizers will come between the polymer chains and will push them apart, reduce the strength of the intermolecular forces, and chains can slide around more, so the polymer can bend. So this is why it becomes more flexible. Condensation polymerization, it's when a water molecule is removed either by the use of a dicarboxylic acid and a diol, or a diacyl chloride with a diol, or a diamine with a dicarboxylic acid like nylon. So nylon is a synthetic polymer that comes from the addition from the condensation polymerization of a dicarboxylic acid and a diamine. Naturally occurring polymers are proteins and DNA. Again, protein came only once over the past 5 years, and DNA hasn't been in the exam at all over the past 5 years. There might be a question on the two types of polymers with a comparison between them, like in type of the disposal, type of bonds, and so on. So remember, for the condensation polymers, there will be hydrogen bonding, but for the addition polymers, there's only the van der Waals bonding. And then I want to go quickly over the important things that you need to know about the naturally occurring polymers in case they show up in the exam. So the questions will not be anything outside these points I'm talking about. The first one is the primary. Remember the primary, secondary, and tertiary structure of protein. So the primary structure is simply the chain of the amino acids, and then the secondary structure are the alpha helixes and the beta pleated sheets, and they come from the hydrogen bonding between the amino acids. And then finally, the tertiary structure is the 3D structure, where there is bend and there is formation of the structure of the protein due to the formation of more of the hydrogen bonding between amino acids are far away from each other in the chain. The type of bonds that we see in the proteins are hydrogen bonding because they have an H and OH. Also, we see what is called the disulfide bond. So the disulfide bond or disulfide bridge is simply is sulfur-sulfur single bond or covalent bonding, and it usually formed between the thiol groups or the SH groups of cysteine amino acids. If you have two cysteine amino acids, they both have an SH group, they form an SS bond or a disulfide bond. Remember that the pH and the temperature will affect all of these type of bonds, so they can change the shape of the protein. Enzymes are biological catalysts, and they have active sites. So if they ask you about enzymes, you have to refer to the presence of the active site of the enzymes. They are stereospecific. What do we mean by stereospecific? Meaning that the enzymes will have this active site or this pocket where the different molecules can bind to. They have to fit inside that pocket, something like the lock and key. So only one key can open this lock. Not every key can open it. So it's more like this. So because the active site as well has amino acids, because enzymes are proteins and amino acids are optically active, or they form isomers of optically active isomers. So they will react with only certain isomers. So one year there was a question why an enzyme catalyzed the hydrolysis of one optically active molecule and not its enantiomer or the other, the mirror image of this, the non-superimposable mirror image of that particular one. And this is because of the stereospecificity of the enzymes. And then DNA. So DNA is a polymer of nucleotides. They have the phosphate group, sugar, and the nitrogenous bases. There is a hydrogen bond between the bases, which is responsible for the formation of the double helix. There are two polypeptide strands. And don't forget that cisplatin is an anti-cancer agent that binds to the DNA, and it stops the protein that replicate the DNA from copying it properly. So in case they ask you about cisplatin and how it's used as anti-cancer agent. In your exam, there will be some practical skills. There usually a question with a practical skills. So in these questions, they tend to ask you about different skills and the use of different reagents. I will go quickly over the most important one that come usually in the exam. So remember, if you add some water, then that means that you are trying to remove the water-soluble impurities in the washing step. So you have a washing step and you add water to remove the water-soluble impurities. If they tell you why did they use this particular solvent, this is because you want to use the solvent to dissolve the things. So if you use something like aqueous ethanol and you have mixture of like water soluble things and organic molecules, then you need to dissolve everything, the organic molecules in the organic solvent and the water or the inorganic things using the water. When you have a flammable solvent, you should use water bath or electric heater. Okay, so because it's flammable, so you don't use Bunsen burner. Add drying agent to remove excess water, so like anhydrous magnesium sulfate. So any drying agent to remove water in the purification step. And to remove the insoluble impurities, you tend to use either funnel, you can use the separating funnel to remove the water soluble impurities from the organic impurities, because you're going to make from the organic product, because you're going to make two layers which are not miscible or immiscible layers from organic product, for example. and from the water. So you can use the separating funnel. You can use the Buchner funnel to remove the insoluble impurities. So the Buchner funnel is when you use the filtration under a reduced pressure. Volatile liquids can be purified by distillation, so we don't tend to use high temperature here. We use distillation, and if the boiling points between the different the products and reactants are very close, or between the different products are very close, or the mixture, then we use fractional distillation rather than simple distillation. Don't forget about recrystallization. How to do recrystallization? Also another method for purification or to purify your solid product. Melting point and boiling points can be used as good indicator for purity because impurities will decrease the melting point of your product, and the product will melt over a range of temperature rather than having a sharp melting point, and it will increase the boiling point. So impurities will increase boiling points, decrease the melting points. Test for functional group for the organic chemistry, quite common in the exam. So the ones that you need to know, the use of acidified potassium dichromate and warming. Don't forget the acidified one that you used acid with the dichromate. So the change of the color from orange to green, you can see positive test for primary alcohols, secondary alcohols, and aldehydes only. And then Tollens reagents, which gives you the silver mirror. Also, we warm with the Tollens reagent. It will give you the silver mirror as the observation. So it's going to be positive for aldehydes, but not for ketones. So this is specific for aldehydes. Or the use of filling solution again was warming, so there will be change of color from blue to give you brick red precipitate. So the observation here, it will be formation of brick red precipitate, and it will be again positive for aldehydes only, not for ketones. So this is again specific for aldehydes. Bromine water test, which is decolorized from orange to colorless. This is for carbon-carbon double bond, is specific for alkenes. And then the use of sodium carbonate is a test for the carboxylic acid, where we see fizzing, and the gas produced here will be carbon dioxide. We can test this gas using lime water. Isomers are typical in the exam, and definitely there will be questions about isomers, whether we are talking here about the Z and E isomers for alkenes, or whether we are talking about optical isomers. So remember the Z and E isomers for alkene, when you have the alkene, the two carbons of the double bond, you have on each of them, there are two different groups. So you have to have two different groups on each of the two carbons. And then you have to assign priority. If they ask you about the CIP rule to assign the priority, you have to refer to the atomic number, not the atomic mass. So it's common that students make this mistake, refer to the atomic mass. We don't refer to atomic mass, it's atomic number. So the one that has the highest priority will be the one with the higher atomic number. So here it's carbon over the hydrogen, and the other one carbon over hydrogen. So the both groups with the highest priority are on the same side. So this is Z isomer or Z isomer. And here in this other one, the two groups with the higher priority are on opposite sides. So that's the E isomer. The optical isomers, which how can we differentiate between two optical isomers? This is a common question in your exam. This is because they're gonna rotate plane polarized light in opposite direction. They are non-superimposable mirror image, so your answer will be rotation of plane polarized light in opposite directions. This is when we have a chiral center, a carbon which has four different groups attached to it, and then we can have two non-superimposable mirror image for the compound. These two are optical isomers. Remember that amino acids have optical isomers because they have the carboxylic acid group, they have the amino group, they have the side chain, and they have hydrogen. So this carbon is a chiral center, and it has four different groups attached to it. Finally, I want to go quickly over these extras. First one is the catalytic cracking. So the question in catalytic cracking comes as complete the equation for catalytic for the cracking, or name the suitable catalyst. So you have to refer to alumina or silica. The impurities that we find and the environmental effect, they tend to ask about the sulfur dioxide. So remember that sulfur dioxide comes from the sulfurs in the and fossil fuel. So when you burn the fossil fuel in air, they will give you sulfur dioxide, and that causes acid rain, which damages building, and they can be removed using the alkaline slurry or calcium carbonate, which will give you calcium sulfide. Calcium sulfide is water soluble. And then the nitrogen oxides, again, they come from the high temperature of the engine in cars. So again, they cause acid rain, and they can be removed by catalytic converters. So you can put the equation as nitrogen oxides, give you nitrogen and oxygen. And then the biofuel. So ethanol as a biofuel. So ethanol is almost carbon neutral, but it's not 100%. So like 2 years ago, there were like 6 mark questions about the use of biofuel and the advantages and disadvantages. So when if they ask you about the biofuel and how it's carbon neutral, you have to refer to these three reactions. First one, that plants will take carbon dioxide from air to produce the glucose, and then the fermentation, which is the production of ethanol from glucose. And then finally, when ethanol is burned, it will produce carbon dioxide. So one molecule of the ethanol will give you 2 molecules of ethanol. So 1 molecule of glucose give you 2 molecules of ethanol, and 2 of ethanol will give you 4 carbon dioxide. However, 6 carbon dioxide will be taken with 6 water to give you 1 ethanol. So in total, you can see that there are the 6 carbon dioxide moles produced and 6 taken in. So it should be carbon neutral. However, it's not 100% because you still need to reduce carbon dioxide to when you use the fossil fuel to operate the machinery that does the filtration and that does all the process, all the different processes for the production of the biofuel. So it's not 100% carbon neutral. What are the advantages and disadvantages? Advantages is that it's renewable energy source and it produces carbon dioxide as burned, but that the carbon dioxide is absorbed by plants while growing. So we say it's almost carbon neutral. The disadvantages is that the